I don't know how it started streaming without me telling it to, but it is 8 o'clock now, so we will start streaming. Okay, so let's look at our first question. So we're going to start off with, it looks like, some optimization questions from here. So we have a and b are two numbers such that a plus 2b equals 20. What is the maximum possible value for ab? So take this away. We have a plus b. Come on. A plus 2b. Something under my pad here. There we go. Equals 20. We want to maximize AB. So our product is equal to A times B. We're going to take this equation here, this A plus 2B equals 20, and we're going to solve for A so that we can substitute this into our product and get a single variable calculus problem. We get A equals 20 minus 2b. We can now plug this equation, right here, into our product equation. We get A is equal to 20 minus 2b, so we get b times 20 minus 2b, which in turn is equal to 20b minus 2b squared. This is the equation we're going to maximize. So, to maximize this equation, we're going to take a derivative. So p prime is equal to 20 minus 4b, and that is going to give us, since we're going to set this equal to 0, that's going to give us 20 is equal to 4b, which in turn is going to give us that b equals 5. Okay, so now that we know that b equals 5, we still know that a plus 2b is equal to 20. So that tells us that a is equal to 10. Now we know a and b are 10 and 5, respectively. And this will also give us that our product is equal to 5 times 10, which is equal to 50. Okay, so that is our solution to problem 1. We know A is 10, B is 5, and the product of the two of them is 50. Problem 2. We're going to have water leaking out of a tank at a rate of R of t equals 200 minus 8t liters per minute, where t is between 0 and 25 minutes. Find the amount of water that leaks out in the first 5 minutes. Okay, so here is our rate at which our liquid is leaving. This is going to use, we're going to use an integral to figure out the amount of water that is left in 5 minutes. Now, we haven't covered, or we just started covering integrals but we didn't cover how to use them to solve problems yet. So this is something that we'll learn next week, but it's something on the final, so we're going to do it now. So the way that we set up this problem is we're going to take an integral from 0 to 5, since we want the first 5 minutes of water flow, okay? We integrate the rate at which the water is leaving, and so that's going to be this R of t is the rate at which the water is leaving. So we go 200 minus 8t, and we integrate with respect to time, because we have a rate that's liters per minute, and what we want is liters. So we integrate against minutes to go from liters per minute to just liters. So this is our integral. We have the integral from 0 to 5, so from the start to 5 minutes later, of our rate, 200 minus 8t, with respect to t. That is going to equal, so this is just a polynomial, so we use the power rule on it, but we use the integral power rule, which is the opposite of the derivative one. The derivative one was we take the power down as a coefficient and subtract 1. This is the opposite. We're going to add 1 to the power and then divide by the new power. So this will be 200 t, because this is t to the 0 here, so adding 1 to the power gives us t to the 1. And then we divide by the new power of 1, so we get 200t. The next one, we have a power 1 on our t, so we're going to go to a power 2. 1 plus 1 is 2. We're going to divide by 2, so we'll get minus 4t squared from 0 to 5. This is an evaluation bar. All that means is we take everything that's next to it, and we plug in 5, and we plug in 0, and we subtract the 0 value from the 5 value. So we get is equal to 200 times 5 minus 4 times 5 squared. So that's, we're just taking this value here, we're plugging 5 into this, so 200 times 5 minus 4 times 5, and that'll be our first term. And then we'll subtract, oh, that's a different blue. That's still a different blue, but it's closer. We subtract off what we get when we plug 0 into this. So 200 times 0 is 0. And then 4 times 0 squared is still 0. So subtract off 0 minus 0. And that leaves us with 200 times 5 is 1,000. Ooh, that's off the screen. Let's fix that. $1,000 minus 4 times 5 squared, so that's 4 times 25, or 100, which is equal to 900. So over the course of 5 minutes, 900 liters escapes from the tank. Okay, so let's look at the next problem. So, find the derivative h prime of this function. So, our function is a pretty nasty one here, to be honest. So let's write it down. We have h of x is equal to 3x plus 2x. 3 to the x plus 2x. There you go. We have h of x is equal to 3 to the x plus 2x over sine of x. So here's our function. We want to take the derivative. Now, here we could either use the power rule, or the power rule and the chain rule. We could use the quotient rule, or we could use logarithmic differentiation. In this case, I think the quotient rule is the best. So the derivative is going to equal cosine x. No, that's wrong. Sorry, it's the denominator times the derivative of the numerator. So we're going to have sine x. And we might need to actually go to another line for that as well. So let's go down here. H prime of x is equal to the denominator times the derivative of the numerator, which is going to be 3 to the x ln of 3 plus 2 minus the derivative of the denominator, which is going to be cosine x times the numerator, which is 3 to the x plus 2x, all over cosine. Sorry, that's wrong as well. The square of the denominator, which is going to be sine squared x. There we go. This is our derivative. And so when we look at the options that we were given, we notice that that is the, it's like the option A to me. No. Oh, I copied it down wrong. Not 3 to the x, it's 3e to the x. Okay. So let's fix that. There's my eraser. Okay. So we have 3e to the x, which is going to be, it's going to change this here, which is going to give us 3 times e to the x. Yep. 3e to the x plus 2. And then here, instead of getting 3 to the x, we're going to get 3e to the x. There we go. This is the derivative of the function, and that was the derivative listed as D. D looks like the answer. 3e to the x plus 2 sine x minus 3e to the x plus 2x cosine x. Yes, that looks like what we got. Okay, so let us look at our next problem. We want to use linear approximation to estimate square root of 1.2. That, when we were, these are all questions taken from drafts of finals from previous semesters. We took this question off of that final, but it might end up on your final, so we will cover it. So we want to estimate the square root of 1.2. So the way to do that is we're going to use a tangent line. That's what linear approximation will mean for us, is we will take a tangent line and we will plug in correct points. So we want the square root of 1.2. So the function that we're going to find a tangent line for is going to be square root x. The place where we're approximating is, or the place where we're going to find the tangent line is going to be 1, because 1 is really close to 1.2, and it's something that we can compute the square root of really easily. So we're going to find the tangent line to this function at this point. That's going to look like this. F prime of x equals 1 over 2 times the square root of x. So f prime of 1 is equal to 1 over 2 times the square root of 1, which is equal to 1/2. We now have a slope. We have the x coordinate of a point, and we plug 1 into f to get the y coordinate, so f of 1, or not f prime of 1, just f of 1. Go. F of 1 equals the square root of 1 equals 1. Here's the y coordinate of our point. So since we have the slope, the x coordinate, and the y coordinate, we can write down a line. Our line is going to be equal to, we have the point 1, 1 that we're going through. So our line is going to be y minus our y coordinate equals our slope times x minus our x coordinate. We solve for y, we get y is equal to 1/2 x minus 1/2 plus 1, which is 1/2 x plus 1/2. And this is our line. So now that we have this line here, this is our linearization. This is what we're going to use to approximate the value at 1.2. And the way that we're going to do that is just plugging in 1.2 into L. So here is L of 1.2. That's equal to 1/2 of x, which in our case is 1.2, plus 1/2, which is equal to 0.6 plus 0.5, which is equal to 1.1, and this is our approximation. Okay, so let us look at our next question. We have values for integrals, and we're going to use them to find the value of a third integral. Okay, so let's talk about this problem. We have the integral of 1 to 6 of f of x with respect to x is equal to 8. We also know that the integral from 4 to 6 of f of x is equal to 12. And the last integral, the integral from 1 to 4, is what we're looking for of f of x. Yes. So this is what we're looking for, this last integral. We know the other three. Now, the first integral, what this integral means is that the area, the net area above the curve between 1 and 6 is 8. So that means that if you look at the graph of this function between 1 and 6, like it might be negative, but what happens is that if you take this area above the graph between 1 and 6 and subtract off this area below the graph, that's a bad color for contrast, that this area on top minus this area on the bottom, so this area on top minus this area on the bottom equals 8. That's what that means. The net area is 8. The area above the graph is 8. So, and the same thing for this integral here. This integral here is, we're going to have okay, so the second integral, the net area between 4 and 6 is 12, meaning that the area above the curve minus the area below the curve equals 12. So this is what we know. We have some function here where the area between above the graph minus the area below the graph between 1 and 6 is equal to 8. And the area above the graph minus the area below the, above the axis minus below the axis is equal to 12 here. Well, what does that mean about the area from 1 to 4, which is this area here? Well, this area above the graph minus the area below the graph is 12. The whole area, the area above the graph minus the area below the graph is 8. So that means that the area that is above the graph minus the area below the graph here must be -4, right? If there's 12 more units of area above the axis than below here, and there are only 8 net units above the axis for the whole region, that means that there must be 4 more units below the axis than above it on the other side. Okay, so we know that this integral here is equal to 4. Sorry, -4. Okay, that's not so bad. I mean, you'll want to check to make sure they don't do anything like this. They might ask you, what's 2 times this? In which case your answer is going to be -8. But it's not all that hard to compute once you know what it's asking for. Okay, so let us look at our next question. Our next question is, there you go, f of x equals this function. On which of the following intervals is f increasing? So let's just figure out where this thing is increasing. Our function is going to be a switch to paint. Okay, so we have f of x is equal to 3x to the 5th plus 5x to the 4th plus 7. So, to find where we're increasing and decreasing, we're going to want to take the derivative. So let's take our derivative. F prime of x equals 15x to the 4th plus 20x to the 3rd. Then we're going to need to know, where is this function switching signs? Where is it positive? Where is it negative? And by function, I mean the derivative. Putting over here, where is the derivative positive and negative? Because where the derivative is positive and negative will directly correlate with where the function is increasing or decreasing. So let's look at that. F prime of x is equal to, let's factor out a 5x cubed. We get 3x plus 4 as our other factor. That means that x, or f prime of x has roots at x equals 4/3 and 0. These are roots of the derivative. These are places where it switches signs. We'll see, well, here's 0, here is 4/3. And because this thing is completely factored, and because it has positive coefficients on its x's, and because the leading coefficient for the whole factored expression is positive, we know that we are positive in the right interval. When we hop over 4/3, 4/3 is an odd order root of the function, so we switch signs, we'll be negative there. And when we jump over 0, 0 is also an odd ordered root. That is, the power on the x term is 3, which is an odd number. Power on 3x to the 4th is 1, which is an odd number. So we'll switch signs. And these are where our derivative is positive and negative. So we are increasing from -infinity to 0, and from 4/3 to infinity. And we're decreasing from 0 to 4/3. So, looking at our problems, it looks like, where are we increasing? -infinity to, oh, sorry. Our root is at -4/3. So let us rewrite this. bad. There we go. This is 0. We have here 0 and -4/3. Still, this thing is factored as a positive coefficient, so we are positive on the far right interval. We jump over 0, getting negative in there, and we get positive out of there, just like we said before. So our increasing interval is going to be we're going to switch these. This is -4/3. This is 0. And switch these as well. There we go. So we have -4/3. 0, -4/3, and 0. There we go. Okay, so we have all of our intervals. Looking at the question that we were given, we have, that is option F. Option F. Okay, so our next question is we want to find the derivative of arc cosine of 2x. Now, if we remember what the derivative of arc cosine is, we can just plug all of this into the chain rule. If we don't remember what arc cosine is, we can use implicit differentiation to solve this problem. Okay, so let us figure out what this derivative is. So we're going to set this equal to y. That gives us 2x equals cosine y, which gives us x equals, well, I guess we don't need to solve any further for x. We can use implicit differentiation from here, so we get 2 is equal to negative sine of y, which is equal to 2, right, is equal to negative sine of, we know that y is equal to arc cosine of 2x, so we get arc cosine of 2x. We want to simplify this. So we're going to draw a triangle. The angle of this triangle is going to be y, because that's the angle in our equation here. We know that the cosine of this angle has to equal 2x. So we need to pick side lengths for 2 of the sides of this triangle to get the right cosine of 2x. So we have cosine is going to be the adjacent over the hypotenuse, so we'll pick 2x for this side and 1 for the other, and that'll give us the square root of 1 minus 4x squared on the other side by the Pythagorean theorem. So, since we want the negative sign of the arc cosine of 2x, that means that we want negative opposite over hypotenuse. This is going to give us that 2 is equal to, or y prime from the chain rule. We're going to get 2 is equal to negative square root of 1 minus 4x squared over 2x. We have a y prime here because when we did implicit differentiation, when we took the derivative of y going from here to here, we need to multiply by y prime. And we solve for y prime. We get y prime is equal to 4x over negative square root 1 minus 4x squared. That's under the... Where's my mouse? There you go. Y prime is equal to 4x over negative 1 minus 4x squared. There you go. Okay, so here is our next question. We have, find the derivative g prime of the function g of x equals x cosine of x. Okay. So with this problem, we're going to use the product rule. So we have, here's g of x equals x squared cosine x. So the product rule says that g prime of x is equal to the derivative of our first function times the second, plus the first function times the derivative of the second. Now the derivative of cosine is negative sign, so we get 2x cosine x minus x squared sine x. So that's just our derivative, and we're done with that question. Let's move on to the next one. We have a function f is defined and twice differentiable on the real number line. F prime of 2 equals 0, f double prime of 2 equals 4. Then, well, then what? So let's look at all of our options. So f has, let's see, does f have an inflection point at x equals 2? It does not, because inflection points are places where the second derivative switches signs. They're places where we switch concavity from concave up to concave down or vice versa. No inflection point because the second derivative is not 0. B, f is increasing in a neighborhood around x equals 2. That's not true. So we have the first derivative equals 0. That means that we know that our horizontal, we have a horizontal tangent line at 2. Our function is not increasing at 2, but it's not asking at 2, it's asking a neighborhood around 2. But we also know that that's false because we know the second derivative is positive. The second derivative being positive means the first derivative is increasing. So what that means is that the first derivative must be less than 0 on the left of 2, and it must be greater than 0 on the right of 2. So it's increasing on the right side of 2, but not on the left side of 2. So we are not increasing in a neighborhood around 2. Okay. What about f has a relative maximum at x equals 2? That is not true because the second derivative test says that a 0 in the first derivative and a negative number in the second derivative is going to lead to a maximum. Positive number in the second derivative means a minimum. So D is correct. It might not be the only correct statement, but D is definitely correct. The second derivative test says that f must have a minimum at 2. Look at E. It says f is decreasing in a neighborhood around x equals 2. No, for the same reason that B is false, E is also false. Because even though f is increasing on the right and decreasing on the left, it's not increasing or decreasing on both sides of 2. And f is false because we have enough information to conclude that D is correct. So that is our answer, and we move on. What is the maximum value of f of 4x squared minus x to the 4th plus 1? Let's write that down. F of x equals x 4x squared minus x to the 4th plus 1 on the interval -2 to 2. Here is our problem, and the way that we do this is we're going to find the derivative, set it equal to 0. That gives us our critical points. F prime of x equals 8x minus 4x cubed. This is our function. It factors as 4x times 2 minus x squared. That means that we have roots at x equals 0 and plus or minus square root 2. These roots are in our interval, so we'll have to check all of these to figure out our maxes and mins. Okay, so first of all, one thing we do know, this is an even function because it has even powered powers. Sorry. Yeah, all of the powers in this polynomial are even, so it's an even function. That means that it has reflective symmetry across the y-axis. Or in other words, the graph looks something like this, where the left side and the right side of the axis look the same. However they look. They probably don't look like this, but they'll look like mirror images of each other, this side and this side of the y-axis. So what that means is we only have to check the numbers on one side of the axis because the values on the other side will be identical. So let's check f of 0 first. That's 1. Check f of square root 2 next. That's going to be 4 times 2 minus 2 squared plus 1. Because square root 2 squared is 2. Square root 2 to the 4th is 2 squared. That's going to be 8 minus 4 plus 1. That's going to be 5. 8 minus 4 is 4 plus 1 is 5. And then f of 2 is equal to, we get 4 times 2 squared is 4, minus 2 to the 4th is 16, plus 1. Well, 16 minus 16 plus 1 is 1. So our options for maximum are either 1, 1, or 5. So 5 is, of course, our maximum here. Okay, so let's look at our next question. Our next question is not on this page, so let's find our next page. Okay, so we have h of x equals, I'm not going to use that color. Here we go. H of x equals f of g of x. And then we're given a bunch of values for f and g and f prime and g prime. So let's see. Did we just make a table somehow? Let's do that. Here is f prime, g prime, and we have value at 1 and the value at, oh no, we have the value at 1 and 2. Are those are the only values being plugged into our function? Okay, so it looks like f of 1 is 3, f prime of 1 is 5, f of 2 is 3, f prime of 2 is 7, g of 2 is 1, g of 1 isn't given, g prime of 2 is 2, and those are all of the values that we were given. Okay, so now we want to find h prime of 2. Okay, here we have our table. This is the information that we need. We know that h prime of x by the chain rule is going to be f prime of g of x times g prime of x. When we plug in 1s for everything, that gives us f prime of g of 1 times g prime of 1. No. We weren't asked for 1, we were asked for 2. There you go. So g of 2, h prime of 2 equals f prime of g of 2 times g prime of 2, which, by our table, we know that we get f prime of, what's g of 2? G of 2 is 1. What is g prime of 2? Oh, that's 2. What's f prime of 1? F prime of 1 is equal to 5. So 5 times 2 equals 10. Okay, so 10 is the derivative the value of the derivative where we're looking. Okay, so the next question, we want to find dy dx for xy equals cosine of y. So xy equals cosine of y. We want to find dy dx. So we're going to take the derivative of both sides. We get derivative of the first times the second plus the first times the derivative of the second equals, get negative sine y prime. Use the chain rule because we're taking the derivative with respect to x, but the variable is a y, so we have to put in our y prime. Now we're going to solve for y prime. We move everything with a y prime to one side. We get y equals negative sine y minus x all times y prime. Because we're just going to take this here, move it to the other side, and then factor out the y primes from both of these terms. That gives us this. Okay, so from here, pick this color, we solve for y prime, so we get y prime equals y over negative sine y minus x. And if you wanted to, you could like factor out the negative sign and bring it to the top of the fraction or whatever. But this is our answer. Next question. So, you know, we don't do epsilon delta proofs on our finals anymore, so I'm going to skip this question. But if you're interested in seeing it, I can come back to it. Okay, so question 14. We're going to suppose that, get back over to paint.net. Suppose that y is equal to 3x minus 7 is an equation of a tangent line to the graph of y equals f of x at x equals 1. Find the values of f of 1 and f prime of 1. Oh, this is actually really easy. So here is our line that we were given. We want to find f prime of 1 and f of 1. Well, what is f prime of 1? F prime of 1 is the slope of the tangent line at 1. Okay, so the slope of the tangent line at 1. This is the tangent line at 1. What's its slope? It's 3. F prime of 1 equals 3. Okay, well, what about f of 1? Well, tangent lines, at the place where they're tangent, they have to actually hit the function there. So if, we have a graph of a function like this, and this is x equals 1 here, whatever value this is, the line has to go through it. The tangent line has to go through this point. So if we just figure out what the value of this line is when x is 1, we have it. So y equals 3 times 1 minus 7 equals 3 minus 7 is negative 4. So this is our f of 1 equals negative 4. Here's f of 1. Here's f prime of 1. And that's the answer to this question. Yep. So looks like f is the answer to that question. Okay. That was a slow-pitched question there. They wanted you to get that one right. Like, we actually want you to do well on the exams. Like, we want to know that our students are actually learning and that they got something out of the class. It's rewarding to know when your class, likes the subject you teach. But that said, we also don't want to give grades that don't reflect knowledge. If you don't know the subject, you shouldn't get an A in it. So we want to write exams that scatter students. The ones that know what they're talking about get good scores, and ones that don't get bad scores. But that means you have to have some questions that, so that C students can get a C on the exam. If you don't have 70% of your questions being easy, then how do your C students get C's? They'd get lower than C's if you didn't have at least, 70% of the questions should be easy. That was an easy question. That was to make sure that the average isn't below a C. Okay, so if for all x you know that 2x squared plus x minus 2 is less than or equal to f of x, is less than or equal to 4x to the 4th plus 2x squared plus x minus 2, do you have enough information to find the limit as x goes to 0? If so, what is the limit? Yeah. So, yes, sorry. So the question was, do you have enough information to find the limit as x goes to 0 of f? If so, what is the limit of f at 0? Okay, so, yeah, this is a squeeze rule question. The question is this limit equal to that limit at 0? Okay, and since those are both polynomials, you know that their values at points are equal to their limits at those points. So we're just going to plug in 0 and see what happens. So we get this side is a negative 2. This side is also a negative 2. Hey, look, the limit of the left function as x goes to 0 is equal to the limit of the right function. I'm just going to call this one g and this one h. And they're both equal to negative 2. The squeeze theorem says this is enough to show that the limit of f as x goes to 0 is negative 2. Oh, and I did none of that on camera. There we go. So, yeah, this function here is g, this function here is f. Is h. Since the limits of g and h are the same, the limit of f is squeezed between both of them to be the same as them. Okay. The next question. We're going to evaluate this integral. So, I think that I'll save this for the next review because I already did one integral question that was something we hadn't covered yet. This one uses u substitution, and bonus points to any of you, and by bonus points I mean bonus internet points, if you solve that one yourself. Okay, so here is a Newton's method question. For the graph shown, if we use Newton's method with initial point x1 equals 0, what will happen? Well, so with this problem, if our initial point is here, then our tangent line looks like it overshoots the root and goes somewhere over here, at which point we repeat the process, find the tangent line here, and it looks like it converges pretty quickly to 1. So the Newton's method process looks something like this. So here's a graph. Have some function on it. Now with Newton's method, what happens is I'm going to take another color. You pick a point, say, I want to find a root. I'm going to pick a point that I think is close to the root because I don't know what the graph looks like. I pick a point, I plug in that point, I find the tangent line at that point. And that line will have a root. It's easy to find roots of lines. So that line will hit a root, and I'm going to guess that that root is closer to the root where I started. It's not always the case. Sometimes Newton's method fails. Anyway, I take that next point, I plug it in, and I find the new tangent line. A little steeper, I guess. There we go. And that has a root. So first I thought this was my root. Then Newton's method gave me this is my approximation, and this is my second approximation. And hopefully, if I keep doing this over and over again, it'll actually pick the actual root of my function, which is this point here that's kind of close to the origin. But you hope that this process of tangent line, tangent line, tangent line eventually allows you to find the root where you cross the x-axis, or this point is another root. Anyway, so looking at the original graph that we have here, it looks like we would converge to the root at x equals 1. That's option C. And I mean, looking at this graph here, it looks like if we picked a point like 4, we picked this point here, our tangent line would pick something further out here, and that tangent line would pick something further out here. So we'd have tangent line, tangent line, tangent line, and this one would go off to infinity, which is what they're talking about with B and D. Going off to diverging to infinity or negative infinity is when you have the function such that it keeps on just picking, every iteration of Newton's method picks a point further and further down the number line. Newton's method fails immediately if you accidentally pick a horizontal tangent line, because horizontal lines don't have roots. Draw a person dabbing. Well, sure. That's what, like this? The person, and then how to hands. Like that. That's a person dabbing. They're looking down this way into their elbow. Okay, so that was fun. And now back to calculus. So, let's look at the next question. We'll evaluate the sum from 0 to 99. Okay, so this sum here is called a telescoping sum. To 99. We have the sum from n equals 0 to 99 of 1 over n plus 1 minus 1 over n plus 2. Now, I'm going to write out a few of the terms at first. So if we plug in 0, we get 1 over 1 minus 1 over 2. That's our first term in this series, plus 1 over 2. So when n equals 1, we get 1 over 2 minus 1 over 3. Plus, and this will go up to, the last terms are 1 over 99 plus 1 is 100. And then 99 plus 2 is 101. So we have, sorry. So we have all of these terms up all the way to these last terms, 1 over 100 minus 1 over 101. What happens is each term cancels except for the very first term, the very last term. So it ends up being 1 minus 1 over 1 is just 1 minus 1 over 101, which is equal to 100 over 101 over 101. There we go. So that is our next problem. The next one is the limit as x goes to 3, sorry, negative 3 from the right of x over x plus 3. So we want to figure out this limit. So notice that we have an asymptote here because the root on the bottom isn't balanced by a corresponding root in the top. So this is going to have this asymptote at x equals negative 3. And we have to figure out, well, is our function positive or negative here on the right side of 3? Well, let's plug. We could plug in points, but what we know is this is a standard form rational expression, which means that all of the coefficients on the x's are positive. This thing is completely factored. That means that the coefficient on the outside of this fraction, the sign of that coefficient determines the sign in the far right interval. It's positive, so we are positive here. We hop over our first root. Our first root has odd order, so we switch signs. The next root also has odd order, so we switch signs again. So we are in fact going down to negative infinity here. Because if we're going to, we know that we have an asymptote, so we're either going up to positive infinity or down to negative infinity. And since we are negative on this interval here, we know we're going down to negative infinity. And if I can draw, it looks like that, going down to negative infinity. Okay, so that's that problem. Look at the next one. Okay. Okay. The following is the graph of a function y equals f of x. Which of the following most closely approximates the definite integral from negative 2 to 2 of f of x dx? Well, if we look at this function, it looks like it's an odd function. What that means is that it's rotationally symmetric. If I were to rotate this whole function around the origin 180 degrees, I would get my original function back. So we know that odd functions integrated across symmetric intervals, and by symmetric I mean symmetric across the origin, 2 units to the left of the origin, 2 units to the right of the origin, they have a value of 0. So the most likely, or the closest approximation to this, based on how this graph looks, is 0. The integral is 0. Okay. So, I am feeling a little sick right now, actually. I don't know if you can hear it in my voice, but I am going to end the live stream here. This is 1 hour's worth of review material. We'll pick this up again. I'm thinking I might be able to do this again on Saturday. So, yeah, I will email all of my students to let them know that we'll be picking this up here on Saturday. And for all of you that would like to see this that aren't my students, you can subscribe and you'll get a notification when I go live on Saturday. So see you then, and